Okay, to refresh your memory, if you remember, we are trying to solve the system of linear equation that can be expressed in the matrix notation as AX equal to B. If the matrix A is symmetrical but not positive definite, then according to my previous lecture, we say we can factorize the matrix A into the form of LDL transpose, as shown in equation 23. So now you can see the matrix A that we have here will be represented as LDL transpose right there. So the next thing that you can do will be to do something like the product of L transpose times X, this product right there. We give it a new name. We call it is equal to the vector Y. Give it a new name. I use this green color there. And therefore, the product from D all the way to here, I use a red color. That red color portion right there basically is the same thing as a matrix D times a vector Y. And that can be represented as a vector Z. So this one here is considered as a vector Z. So as you can see, according to this procedure, then the first thing we can do will be from this equation. As you can see, we can solve for, let's say, L, lower matrix, multiply with the vector Z, the red vector. That should be equal to the vector B. Then, after solving for the unknown vector Z, the next thing we can do is from this equation, we can solve for the vector Y. Solve for the vector Y from this equation. And then, after that, knowing the vector Y, we can use this equation here to solve for the vector X, which is the original unknown vector. So, according to this procedure, I will say that step number 1, which we call factorization, we try to obtain the matrix L and D. That is step number 1. Step number 2, we will try to use this equation. This is called step number 2, which is the so-called forward solution step. Forward solution step, in order to solve for the unknown vector Z. After that part is done, then we go to this equation here, which is called step number 3. This step we can solve for the unknown vector Y, and this phase is called diagonal scaling. Diagonal scaling. That's step number 3. And then the last step, it will be step number 4 that we are going to solve in here. This is step number 4. And this step we call it backward solution. Backward solution. Okay? So those are the sequence of steps that we need to do. Step 1 first, then step 2, then step 3, and then step 4. Now, in my previous example, I already go through the so-called step 1, and I just finished step 2 in the previous slide, in the previous lecture. So with that much of the background, let me move on to the numerical example. Let's take a look at the numerical example. Let's see. In the numerical example, as you can remember, right? If you are given the matrix A and you're giving a vector B, then according to the first step, we use those formula for the diagonal matrix D and for the lower matrix L. We can calculate column 1 of the matrix D and the matrix L. Then after that, we calculate column 2 of the matrix D and L. Then after that, we calculate column 3 of the matrix D and L. And by now, we know the answer for the matrix D and the answer for the matrix L. And that concludes the step 1, which is factorization phase. Step number 2, which we are trying to do right now, step number 2, the forward solution phase. And the L matrix is known, the vector right hand side B is given, and therefore we can solve for the unknown Z1, Z2, and Z3. By looking at the first equation, we can solve for the unknown Z1. Looking at the second equation, we can solve for the unknown Z2. And looking at the third equation, we can solve for the unknown Z3. And therefore, in general, we can use equation 32 that we give you here in order to solve for the unknown Zi, where the subscript I could be 1 or 2 or 3. So this will take care of step number 2. So by the end of step number 2, we were able to solve the unknown Z1 is equal to 1, Z2 equal to 0.5, and Z3 is equal to 0.333. Then move on to the next step, which is step number 3 that I told you earlier, step number 3, which is about diagonal scaling. In this step, basically, we have to solve for this equation, dy equal to z. And please remember, the matrix D we already know from step 1. And the vector z, the intermediate vector z, we already know from step number 2. And therefore, in this step number 3, our objective is to figure out the intermediate vector unknown vector y. In the long form notation, that equation is represented by the system matrix equation as shown right here. So from this system, you can see clearly we can solve very easily for the unknown y1 first, which is equal to 1 divided by 2. And then we can solve for the unknown y2, which is equal to 0.5 divided by 1.5. And then lastly, we can solve for the unknown y3, which is equal to 0.333 divided by this number here. This step is very straightforward and very easy, and that's why I call diagonal scaling. So at the end of this step, we were able to solve for the value of y1 equal to this much, y2 equal to 0.333, and y3 is equal to 1. So this is the end of step number 3, which we call diagonal scaling. After that part is done, the next step, which is the last step, which we call step number 4, is called backward solution phase. Well, in this backward solution phase, the equation that we have is L transpose times x equal to y. And please remember, the vector L we already got from step 1. The vector y we already know from the step number 3. And therefore, from this system equation, we can look at equation number 3 first to solve for the unknown x3. And then after that part is done, we look for the second equation. We can solve for the unknown x2. And then finally, we look at the first equation here. We can solve for the unknown x1. And in general, all of those unknown x1, x2, 3, or actually, we can solve for the unknown x3, then x2, and x1 using this kind of formula. And that is shown in equation 28. So by looking at those formula, we can get the answer for x3, the answer for x2, and the answer for x1. And they are given here. And that concludes this chapter. Is that okay? Yeah, this